Good afternoon, all, and welcome to section 7.4. We're doing the second half, and this is going to be talking about electric potential and electric potential energy. And we start with the definition of electric potential, which is a bit of a review from previous grades in science, and we look at the unit, which is volts. And electric potential is the value in volts of, shouldn't have enough comma there, in volts of potential energy per unit positive charge. For a given point in an electric field. And we can calculate the electric potential V is the potential energy per positive charge in that electric field. A couple of things that we should note in this case. Potential is a scalar quantity. The potential is independent of the amount of charge at a location. It depends only on the electric field strength. The unit for electric potential is the voltage, and the volt is named after Alessandro Volta. And note that 1 volt is equal to 1 joule per coulomb, and the joule is also a Newton meter, so it's also equal to 1 Newton meter per coulomb. The units for an electric field can be expressed one of two ways, either as newtons per coulomb or volts per meter. Both ways work for expressing the units of an electric field. So our electric potential difference, delta V, is the amount of work required per unit charge to move a positive charge from one point to another in an electric field. So what that tells us mathematically is that our electric potential difference, delta V, is equal to EE over Q. Again, this is a scalar quantity, and again, the unit is the volt. In a uniform field, using the above equation, and the fact that the change in electric potential energy is equal to negative E Q D, we get an expression for our change in our electric potential difference. Delta V is equal to negative epsilon delta D. You might ask, where did our Q value go? You'll notice that Q will be on the numerator and the denominator when we substitute, so they simply cancel out. So, if we're given a, let's say, very long-winded problem, as the one above here, in example 1, where we have an electron in the old-style computer monitors leaving a negative plate and accelerating towards a positive plate. Excuse me. And we have electric potential difference between the two plates given to us as 1.8 times 10 to the 4 volts. We can use the law of conservation of energy and the definition of electric potential difference to calculate the speed as it reaches the positive plate. And we shall assume that the electron is initially at rest, and we're given that the mass of an electron is 9.11 times 10 to the negative 31. Remember that the charge Q of an electron is negative 1.6 times 10 to the negative 19 coulombs. So the mass as given, 9.11 times 10 to the negative 31 kilograms. Our electric potential difference, delta V, 1.8 times 10 to the 4th volts. And we're given that it is initially at rest. What we will be calculating is the final speed, Vf. And from the law of conservation of energy, we get the change in electric potential energy plus the change in kinetic energy must be equal to 0. And very similar to yesterday's lesson, if we were to rearrange, what we end up getting is that our speed, in this case final speed, will be equal to negative 2q delta V all over the mass m. Substituting in all these values here, we get that Vf is equal to the square root and substitution of each value and all of this will be divided by the mass m as follows. Using our calculator, we get an answer of that would be 79,515,547.43. In the question, we see our lowest number of significant digits, 2, round to significant digits, so 8.0 times 10 to the 8.367 meters per second. Meaning that at the positive plate, this is the speed of that electron, which was initially at rest. Part B, we're looking to calculate the magnitude of the electric field if we have a separation between the plates of 16 centimeters. So that separation, 16 meters, we still have that same potential difference of 1.8 times 10 to the 4th volts. We're going to calculate the value or the magnitude of that electric field. And recall from earlier, we know that the electric potential difference is equal to the negative of the electric field strength, delta D. Solving for epsilon in this case, we get that it will be equal to negative delta V all over delta D. So that will be negative 1.8 times 10 to the 4th, all divided by 0.16. 112,500. 2 significant digits again, so 1.1 times 10 to the 5th. I forgot my negative sign. And remember that our field strength is measured in I just completely forgot. I believe it's newtons per meter, but now I'm just drawing a complete blank. So let us quickly remember what it is. And just a quick check, it was actually, sorry, I had my meters mixed up. It is newtons per coulomb for our electric field strength. And what does this negative sign tells us? What does it tell us? The negative sign tells us in this case that the field extends from a high potential to a low potential. I hope both those examples are pretty clear and that for the most part it does make sense.